Hi, I'm going to talk about WebGL, Three.js, and I'm going to throw in some React. My plan is to very briefly introduce myself, to give you some basics of Three.js. Then I'm going to talk about Three.js integrated with React. Those bits are less interesting for me. The more interesting for me is when we get to the Three.js and WebGL, or GLSL, because that's where interesting stuff, complex stuff happens. And then I'm going to indulge in some speculation, if you will allow me, if I haven't been booed at that point. So this is me. My name's Alec McEachran. This is my history, more or less. I am a self-taught coder. I was a history, maths and philosophy teacher. I was a Flash web developer. I did a bit of Unity development. Then I joined YouTube in 2013 over in California. I moved back to London, worked in Google Firebase, and I've recently moved back up to Edinburgh, where I'm now principal developer at KPV Lab. And you almost certainly haven't heard of them. And there's a good reason for that, because we're stealth, according to my boss, who's over there. And I'm definitely not allowed to talk about anything that we're working on, except to say that it maybe has some parallels with what I'm talking about today. So if any of you are interested in WebGL, we are also hiring. Who'd have thunk it? So let's talk about some Three.js basics. I'm not going to give you a tutorial on Three.js, because if you want a tutorial on Three.js, you should go to the Three.js website and click on the button on the left-hand side of their page, which says Intro to WebGL with Three.js, and follow that tutorial, because it's very in-depth, it's very good. I recommend it heartily by David Scott Lyons. There is no point in me rehashing that. It would be a waste of everybody's time. But I will try to give you a hello world of sorts. So I'm going to say there are 7 entities in Three.js. Now, I said it was 8 earlier, but I've just changed my mind. There's renderer, camera, and scene. A renderer is the thing that does the drawing. Camera is your perspective. The scene is the universe. Then there are meshes, geometries, and materials. Meshes are essentially objects. Materials and geometries are the things that constitute objects. So you have geometries are sets of vertices or positions, if you like, and triangles, essentially. And materials are the way that those triangles look when they are rendered. And then there are lights. And I decided that shadows aren't really an entity, so that's why I got 7. And lights, obviously, well, self-evident, I suppose. So here is a hello world. There's 5 platonic solids and a backplane with a light casting a shadow. Oh, excuse me. And that's pretty much as basic as you can get, showing most of the things that Three.js gives you out the box. There's some transparency on the object, so you can see the shadow going behind. This is pretty easy to set up. So let's have a look at it. This is simplified. I'm just avoiding any kind of boring boilerplate. But yeah, you need to set up a WebGL renderer. In this context, you need to say that the shadow map is enabled, and then you need to add it to a canvas element. We'll get back to that in a minute. Then you need to construct a camera, and you need to give it a position. You need to give it a field of view, which is the angle at which it sees the world, and an aspect ratio if you don't want things to look skewed. Then a point light, which is just one of the many lights you can have. And you add that. And then in this case, I've got a box geometry, which is also known as a cube. And I've given it a physical material with some properties. And then I add those to a mesh. And then I add the mesh and the light to the scene. And then I render the scene. And that is it. Everything else is an extrapolation from that. The platonic solids you just saw is essentially that with 5 meshes or 6 meshes instead of 1. So far, so simple. So putting that into React also happens to be quite simple. The most simple way you can do it is just by defining a canvas element in your component. I'm not sure whether the Whether you can see the rest of the code in there, unfortunately, well, it doesn't really matter. So you create a canvas and you reference the canvas. And then when you've got the reference, you say, hey, renderer, attach yourself to this, and away you go. That really is a kind of minimal interaction with React. Of course, React has this DOM structure, and Three.js works via the GPU, and so it doesn't attach to the DOM. So we just need this one entry point, and at that point, really, you've got two parallel worlds. You've got Three.js working on in the canvas, and you've got React can do whatever it wants. It can add things over the top. It can be underneath. But there are some options if you want to try to integrate React a little more closely. You can use React 3 Fiber. It's one that I looked at. I'm not convinced about React 3 Fiber, but let's have a look at how it works. I'll go down to this one first, which is that you can define a canvas object, and then you can be all declarative, because React likes that. And you can say, I declare a point light, I declare a box geometry, I declare a physical material. And then you can say, for the things that it's given you out the box, you can use a hook and say, OK, GL, which is what they call renderer for some reason, scene and camera, these are the properties I want to give you. And so that's quite a neat way of doing things. Except that you don't really have to go much beyond the simplest example, and you find that you can't use the declarative structure anymore. Because if you want to do anything interesting, you hit a boundary. And I don't really understand why you'd want to use React 3 Fiber when you're going to have to learn the declarative structure, you're going to have to learn Three.js, and you're going to have to learn WebGL. If you're couching that inside React anyway, why bother with the React 3 Fiber? Excuse me. It just seems like one thing too many to learn. So that's the React bit, which I felt like I had to put in for this. Yeah. More interesting, WebGL. Now, WebGL is a standard technology. It's essentially, if anybody knows about this stuff, some of the things I'm going to put down here are technically wrong, but run with it. It's right enough. It's a tunnel into your GPU. You can think of it like that. It bypasses the DOM. Here's a more interesting example. I've tried to come up with a simpler example that goes from the platonic solids and then is an intermediate step before you get to something really advanced, and this is where I got, but it's still quite advanced. We've got one cube here, but we've got 160,000 positions and 160,000 colors. Imagine trying to put 160,000 divs of any description on a web page. And you start to get an idea. This is running at 60 frames a second, or at least it does in normal conditions. I've also got some simplex noise running, which is a kind of a noise that isn't completely random. It has some structure to it. And it's 3D, because although it's 2D on the plane, the third dimension is time, which is changing. So as I pass it a new time value, the noise distorts, but it distorts gradually. So what you're looking at is the distortion. And then when the distortion drops beneath zero, I change the color. I actually flip the blue and green components of the color, and I also flatten it out. This is running 1.3 million vertex calculations a second. Sorry, per frame. So 77 million a second, assuming it's running at 60 frames per second, I think. OK, no one's going to. Is everyone going to trust me? OK. So I'll have a look at that. This is a slightly more involved example, but roughly this is what is happening under the hood. And this is how we can get such crazy performance out of WebGL and Three.js. So I am using Three.js for this example. Three.js gives me lots of stuff, but I can't do it all. What it's doing is, so what I'm doing is I'm building an instanced buffer geometry, which is just a fancy way of telling the GPU, you've got one piece of geometry, but you're going to use it a ton of times. And then underneath, I'm giving it a whole bunch of data that says, here are the 160,000 positions, here are the 160,000 colors. And then I get to the material, and what I do is I just take a common or garden material and use a hook called onBeforeCompile, and then rewrite the GLSL code. And so this is, to do anything interesting with Three.js and WebGL, you end up having to write some GLSL. There's no avoiding it. And so we'll have a look at that. So think of GLSL as a big loop, right? This is going to run. First of all, I said that there was a cube, so that's 8 vertices, 4 at the top, 4 at the bottom, 8 positions. And I said there are 160,000 positions in the grid. That's 400 by 400 on that grid that you saw. So for each of those 160,000 positions, there's a position and a color. And then for each of those 8 vertices, these 4 eaches are pseudocode, by the way, just in case anybody's curious. We're going to compute some simplex noise, and we're going to work out what height is at that position. And this is, I've removed the get color and the get position because the actual mechanics of that aren't that interesting for the purposes of the talk. But the point being that the GLSL is like this massive for loop that you only get to write the inside of. And so that's important for explaining why GPUs are fast. Because the positions, and then once it's calculated the positions, it calculates the colors for every pixel on the scene. They're all calculated in parallel. Which is why you only get the inside of the for loop, because it's not really a for loop, because it's not all running one after the other. Massive amounts of the vertices are getting calculated at the same time in parallel, and then massive amounts of the pixels on the screen are getting calculated at the same time in parallel. And we're not sure how many, and we don't really care, because GPU architects have worked that out for us. Oh, I think I labeled that point. And that means we have to think slightly differently. If you think about JavaScript and you want to get the color, now I told you that I flipped the green and blue position earlier. So what I say is, if the scale of our bars at every point is greater than 0, return red, green, blue. Otherwise, return red, blue, green. In GLSL, we usually don't think that way. And it's quite confusing why to start with. And so this is just one insight into the way GLSL makes you think differently. And I'm not really going to go into any others, but this one will suffice as there are lots of other dragons here. So what you do with GLSL is you calculate both, whether the scale was greater than 0 and whether the scale was less than 0. And you calculate both results. And then you multiply 1 by 1 and 1 by 0. So you're doing all the calculations for both sides of the conditional, for every vertex and every vertex in the cube and at every position, which seems insane from my perspective as a JavaScript engineer. Why on earth do you do all of that extra work? Oh, I didn't put a slide to say why. I just have to tell you. If you write conditional logic, the shader can't tell whether or not all of the branches are going to finish at the same speed. And this is critically important, because things that run in parallel have to wait for each other to finish. So if you tell your code, if you write your code in such a way that it's guaranteed to finish at exactly the same speed, then there's a whole bunch of logic that it doesn't need to do. Check to wait whether all the other pixels or all the other vertices have finished calculating. When you remove that overhead, you get a big performance gain. So the massive parallelization means that you have to think in a completely different way. So that was my medium example. My friend David Lennertz is a lot better at this than me. and I wanted to show you something that he does. And I don't know if that works. Does that work on the big screens? It works pretty well. Well, David's a wizard. I would like to be a wizard. I like this demo because it looks like me, at least from that angle. Yeah. I mean, this stuff is crazy hard, but I like it because I want to think back to the platonic solids that I showed you, which was WebGL, Three.js, you create a camera, you create one light, you create a renderer, you create one object with one geometry. Admittedly, this is quite a lot more complicated geometry, but it's still just a geometry, still just a bunch of triangles, and one material. And that's the bit where I'm cheating, because David doesn't just use one material. He does a lot of crazy magic that has like 6 materials and 3 render passes to make it look like this. But fundamentally, he's taken the building blocks that Three.js gives you, and he's put them all together in a very simple way, and then he's just tweaked that one bit to make it look like skin. And there's no skin shader that you can download and use, unfortunately. You have to learn that stuff for yourself, or employ David. Or me, maybe. Oh no, come work with us. Sorry, Tom. Whoops. Okay. So we have someone from Formidable who made Spectacle, and maybe he can help me work out why it's not going to the next frame. No. Okay. Why won't it go to the next frame? If you're interested in this stuff, check out Three.js. They've got a ton of amazing examples. You can look at all the source code from all of them. Also check out Shader Toy, which is not Three.js at all, actually. It's just WebGL. They are amazing. They're kind of people who come from the demo scene. They're like mad shader hackers who can do incredible things, and you would not believe some of the stuff's technically possible on that website. It's absolutely stunning. So I told you that Three.js gives you this toolkit for building 3D scenes, and I told you that Three.js React 3 Fiber removed some of the boilerplate, but hopefully I also told you that I don't really buy why you'd use it. I have high hopes for it. I'd like to see it get better, but I wouldn't use it personally. And I also told you that for complex work, I recommend that you use GLSL. I recommend that you use. You are going to have to learn to code some GLSL. But I didn't talk about why, and that's where I'm getting to be a bit self-indulgent, if you'll bear with me. And so I actually wanted to talk about this because of the why, but then I started writing the why, and then I put the why at the end in case, I don't know, in case we ran out of time or something, but I'm going to go with it. I was thinking about the Google Stadia and other recent developments that are moving to computation to the cloud. And I don't think it's going to happen today, and I don't think it's going to happen quickly, but I think that we are moving towards computation going to the cloud generally, and our devices becoming essentially dummy screens that accept input and stream and render streams. Now, I did say this was idle speculation, so feel free to disagree with that. But I don't see that there's any reason to believe that front-end development and web development is fundamentally any different from gaming. There'll just be a massively less amount of data passing through each frame because websites are relatively static compared to relatively dynamic games. And if that's true, then there won't be any constraints. You won't be constrained by the DOM model. You won't be constrained by the power of the devices. One stream is just as good as another. If they can render Netflix, they can render anything you can send to them, right? Which means that you could integrate video, you could integrate text, you could integrate games, you could integrate any kind of interactivity you can think of all together on a web page without any problem if you're doing all the rendering in the cloud. And if that's true, maybe you also build your websites with Unity or some other platform. Any which way, I personally think that this might happen, and if it does, I would want to know about how to do some 3D rendering, because I think it's going to become more important. So that's my sales pitch for why. And if you have any inclination to agree, maybe you should come speak to me and come work on some of the stuff we're doing. Thank you. I think that's me. Yeah. Hooray. I have to admit, I have absolutely no clue for how long I talked, so I don't know. Okay, sure. Anybody want to ask a question? Yes, sir.
See, in perspective to rendering 3D on a browser, what methods do you use to actually test if it's whether necessary to, let's say, render a texture in high resolution, or for example, self-scattering layers like such on a face there? How would you actually go about to elaborate that process to analyze the device and render what's really comfortable to not lose frame rate?
So how would I test the ability to render devices, to render complex models or something on a device?
That the device can handle.
Yeah. So my future scenario, this goes out is not a problem, right? Because you just throw compute power at it at the server side. My today answer is that's a really hard problem. I mean, it is. When I worked at YouTube, we had smart TVs, and we were trying to render video to them, and we had banks of smart TVs with quality assurance engineers working on that problem full time for the entire time I was there, and they still hadn't got a good answer. I mean, they had a pretty good answer, probably better than anyone else at the time, or maybe Netflix, I don't know. But I mean, yeah.
For example, like for video rendering, like YouTube, they would throw a very low resolution video until it picks up something.
Oh, I see what you mean. Oh, I'm sorry. Yeah. So what you'd want to kind of down sample. Yeah. So you can use bitmaps and different sampling mechanisms in materials and textures for WebGL as well. So you can actually throw a low resolution renderer and then throw a better resolution renderer, and then you can detect frame rates, and you can downscale or upscale as you want. I mean, like all the.
So there is a back source to read the frames as a return.
Yeah, I mean, you're not going to get anything out the box, but yeah, you can do that. I mean, that's not a technical constraint. Yeah. Yes, sir.
Yeah, you mentioned dragons, and with GLSL, there certainly are a few dragons in there, and I wondered if you could comment on your debugging workflow.
Oh God! I asked Tom. I mean, in all seriousness, I asked Tom.
Right.
He's much better at it than me. I'm still learning.
Nothing's changed in the last few years then?
No, so he always gets me to, nothing's showing up, and I expected it to. So you go to, okay, find the little branch of code where you think the problem is, and return red if it has a value that you're expecting, and then suddenly the whole screen goes red, and you go, yes, okay, the error is downstream of that, and then you binary search manually through your code until your soul is dead on the ground. Yeah, there is no good. There can't be a good solution to this, right? I mean, unless there's a very good CPU emulator for the work you're doing in the GPU, maybe. But I look in hope that someone might make one, and nobody has. So I guess it can't be done. There was somebody at the back, but I didn't. Yes, sir.
How mature the 3.js is?
How mature is Three.js? Well, so they're at version 0.6 or something. Sorry?
103 version.
Oh, is it a version 103? Oh well, all right. So what I just said, that's all nonsense. Mr. Doobie, who wrote it, who built it, was also building this for Flash back in the days. So in terms of how mature the thinking is that goes behind it, I'd say it's extremely mature. They made a few design decisions early on that I know that a lot of the people in the community don't like very much. So things like big mega shaders that have lots of if-defs in them, which means if you're making a physical material or Phong material or something like that, it's only using half of the shader, but if you want to change it, you're going to have to wade through the whole source code, and that makes it very hard to do things like the on-before-compile rewriting of the shader source. That stuff's not changing because it's baked in. It's an API now. Maybe if they'll do a, well, maybe they will. Maybe they'll fix it. But that's a roundabout way of saying it's pretty robust. I mean, there's lots of people using it in production. So.
I mean, besides your company, is there any organization using the product for them?
I can't speak to anyone specifically, but I know that a bunch of the car customization websites that you see that have 3D cars that you can spin around, you can change different things. I know a lot of those use it, but I couldn't tell you which ones off the top of my head. But yeah. I mean, there are people working on it in production. You can, if you go to the Three.js website, you can also see a whole bunch of smaller scale examples. Yeah, is that it? Oh, yes, sir.
Two quick questions. One, you mentioned that even in your Medium example, you still had to write GLSL. What does Three.js actually give you that you don't get from just building WebGL?
Yeah. So.
The second question is just, if you're building applications based on this, how do you integrate automated testing, end-to-end testing into your application? How do you solve that problem?
The first question. Tell me the first question again.
What does Three.js give you over just WebGL?
Yes, let's you do them one at a time. That's great. What does Three.js give you that WebGL doesn't give you? A whole bunch of tools. So the example that I gave you, the Medium example, I did have to write some GLSL code, but I didn't have to rewrite all of it. I created an instanced buffer geometry instance at the top, a sort of class that I called. And essentially that was a way of telling the shader, oh, you're not just going to run this for the 8 vertices in the cube, you're also going to run this 160,000 times for each of the positions on the plane. For me to have to do that by hand means that I have to remember all the WebGL calls, and WebGL is this horribly stateful thing, and it's quite hard to remember what you've told it and when you've told it. It's hard to manage. I would not recommend doing it from scratch. Maybe people more expert than me, Three.js is a overkill, but for me it's a necessary crutch. And then the second question.
Yeah, but just how do you integrate any kind of end-to-end automated testing into a pipeline or whatever?
Yeah, I feel like that was the same as the first question, which is it's really, really hard.
If you don't know the answer, that's
Yeah. I don't know. If you have a good answer to that, you should come work with us. I don't have a good answer for that right now, but it's something worth thinking about. Yeah. Sorry, that's the best I got. Am I done? Oh, yes, sir.
So you mentioned earlier about rendering from the cloud.
Yes.
Yeah. Is that because there's an opportunity, you think, for blended content to come?
I think that we'll end up rendering from the cloud because I think that the economies of scale mean that it's going to be far more cost effective for big companies, the big FANG companies, my former employer, to have massive banks of the best hardware for doing this stuff. And it's much, much cheaper for them to have massive banks of it than it is for each of us to have one of them in our mobile phone. So if our mobile phone is good enough to render a stream of pixels that come down, then it's going to be cheaper for everybody for those pixels to be calculated on the cloud and sent to me through the Wi-Fi. Now I think that's a relatively radical opinion that I have no good justification for except Google Stadia and the inevitable Microsoft follow-up and And just the history of the web so far is a history of people doing it on local machines and then that compute gradually getting moved to cloud services. And I don't see why you should think that front-end rendering is categorically different kind of compute. So I think, yeah, all compute goes to the cloud eventually. That's just a hunch, an educated hunch. Oh, yes.
Just to follow up from that, how do you solve the problem of latency?
Yeah, how do you solve the problem of latency? Yeah.
Computing everything on the cloud and then sending it to a device instead of rendering it, that's all fine, but it's going to take some time to send to that device.
That is true.
If you're playing a game or something along those lines,
Yeah.
you go, I want to punch the person now. Oh wait, it happened a few seconds down the line.
Yeah, so the question is fundamentally, how do you solve the problem of latency? I don't know. It would appear that people are confident enough that really good edge servers distributed in all the places where people want to play games and really good Wi-Fi and really good broadband has reached a threshold such that people are willing to put major amounts of money behind bets that they have solved that problem, and I don't want to disagree with them. So, yeah. But, yeah, I don't know. If I knew, I probably wouldn't be standing here. Let's face it. So.
Slightly you confused me with this, your futuristic conclusion. That,
Oh, apologies.
I just wonder if this happens, would you still be able to use Three.js or WebGL, because everything is aimed to be rendered on the cloud, so
Yeah.
would be any use for them?
Yeah, and I'm guessing this is probably my last question. So the question is, if my future speculation nonsense is true, then would we still be using Three.js? And the answer is probably no, but we'd be using something relatively similar. We'd probably be using its descendant, or a descendant of Unity, or a descendant of one of the other 3D engines, and they're all relatively the same, at least from our perspective as people who might want to learn this technology, the first principles of this technology. Like, I don't think there's much difference in building a website in JavaScript or I don't know. I mean, anything I say right now might yeah. Well, let's say JavaScript and TypeScript because that's relatively safe. I mean, it's also relatively weak, isn't it? But yeah, I don't think that the technology itself is super important in the long term. But right now, I think it's the best one that I've seen. No, I don't know. I feel like I fudged that too. Am I done? Can I get out of here? Thank you.